A block of mass m, 1.5 kilograms, is released from rest at a initial height of 1.5 meters on a frictionless inclined plane that makes an angle of 35 degrees with respect to the horizontal. Right over there. At the bottom of the inclined plane, the mass encounters a frictionless surface. Okay, so this is frictionless and that's frictionless. Oh, okay, as labeled. Of 2.5 meters. Does that matter? After sliding across the horizontal surface, the mass goes up a second incline that makes an angle of 35 degrees. Check. With respect to the horizontal, has a kinetic coefficient of friction of 0.45 and a static coefficient of 0.52, which is a little bit bigger and that kind of makes sense. What is the maximum height, h max, that the block reaches on the right ramp? Okay, so this is going to be a conservation of energy problem. So we start with some energy. We're going to call it EP initial. And just to kind of feel complete here, I'll also include the kinetic energy initial. And that'll equal energy potential final plus energy kinetic final. That looks like an R. There we go. And we'll add in the work due to friction, basically the resistance pulling it backwards. And I think it's a plus, but it might be a negative. And we'll kind of reason it out as we go. Green. So we start off at rest. So 0. I think it starts out at rest. Yep, from rest right there. And it's going to come to a stop before it comes back down. So what's the maximum height? Maximum height will be when it stops and comes back down. So at that point, the kinetic energy will be 0 before it comes back down. And so what we're going to have then is we're going to have a change in energy potential. So this one minus that one will equal work due to friction. So this will be mgh, mass times gravity times height, is potential energy due to gravity. But I'm going to write this as, I'll write this as h. Actually, I'm going to leave it kind of h initial minus mass, gravity, height, and I guess I'll call this max. So I probably could call it final. Equals, and then this is going to be the work due to friction. So friction is the normal force normal, times a coefficient of friction. And this will be K, because it'll be moving until it stops. So we need to find out what this normal force is. Now, this, you can do it through geometry, but it's mg cosine theta, where this theta right here. This force, the force due to sliding gravity pulling it down, will be mg sine of theta. It's easier just to memorize that. I use the mnemonic sine for sliding, and then I know that the other one is going to mg cosine theta. One way to kind of check to make sure you're right is if theta equals 0, then you have the old standby where force normal will be mass times gravity, which kind of makes sense because cosine of 0 is just 1. Okay, so now we do this. Force due to friction will be, don't need that random line, mg cosine of theta times mu k. Let's see, force, yep, that seems reasonable, but we also need it to be an energy, because these are energies, this is a force. So work equals force times distance, actually F dot dr, that's terrible, but we have a constant force, because our force is mg cosine theta, and theta is not changing. So this is going to be work equals force times distance, and so we need a distance here that it travels. Well, that distance here, I'm going to draw a new triangle over here. It's going to be something kind of like this. Different color to show I'm changing thoughts. We want it in terms of h max, and we also have theta. So we have a hypotenuse there. I'm just going to call it hip for hypotenuse. So this is what? Sine of theta, SOHCAHTOA. SOHCAHTOA is kind of how you memorize, or is a mnemonic for keeping sine, cosine, and tangent straight. So this looks like it's going to be sine of theta. So sine of theta equals opposite over hypotenuse. So rearranging this, hypotenuse, which is the distance we're looking for here, will be opposite, which is going to be h max over sine theta. Okay? So now we know this right here is going to be, see if I can get everything in frame. I don't think so. H max over sine of theta. Okay, so now we have this long equation and we should start simplifying. So everything has a mass times gravity in it, which is convenient, so we're going to cancel that out. We want to find h max because that's what we're looking for. So we want to get them all on the same side. So we have hi equals cosine of theta times mu k over sine of theta plus h max. Oh, and then there's multiplied by h max over here. Yeah, that's okay. I'm going to rewrite that in a sec. So then we have height initial equals, I'm going to write this as mu k over tangent of theta, because that's mu of k is coefficient of friction, but then sine of theta over cosine of theta is tangent of theta. This would actually be cotangent, but I feel more comfortable with this tangent. Plus 1, we have h max here. Rearranging one more time, hopefully one more time, hopefully only one more time, we have h initial over mu k tangent of theta. This is looking complicated. Plus 1. Okay? Can we do this? I think we can do this. And then theta we know equals, was it 35? 35 degrees. So theta, 35 degrees. And mu of k is 0.45. Mu k, 0.45. Okay? Turn on the calculator, clickety-clack, make sure we're in degrees. So I'm going to start at the bottom of the equation, just to kind of keep everything straight. So we have mu k, which is 0.45, divided by quantity tangent of 35. Is that good? Yep. We'll add 1 to that, and then we'll do h initial. What is h initial? 1.5? 1.5. 1.5 divided by second answer, and I get 0.913. Whoop, 0.913, and then this will be in meters. So check out what our possible answers are. Yep, it's even the first one, which is convenient. Whoop, 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 right there, 0.913. So what is the maximum height? H max, the block reaches on the right ramp. It's true, yep. After reaching H max, this is a kind of it's a cumbersome problem. It's reasonably challenging. After reaching H max, the block slides all the way down the ramp and back across the frictionless surface, stops and remains in position, slides partway down the ramp, and then comes to a stop. Okay, so I'm first by drawing a picture. Then we'll evaluate this based on the data given. Whoop, blue. So we have a block. So after reaching its H max, it comes to a stop. So this one doesn't really make any sense. Slides partway down the ramp and then comes to a stop. It doesn't make any sense because this whole ramp is all the same. So if it's at a stop here, there's no reason for it to start moving again and then stop. That just feels weird. So I'm going to say that's not true. So we basically have stops and remains where it's at, which would make sense because we're converting from the kinetic coefficient of friction to the static, which is bigger. And so it might come up there, stop, and then that's it. Slides all the way back down the ramp and back across the frictionless surface. So basically if it's sliding down the ramp and it gets to the frictionless surface, it can then slide all the way across. Not a big deal. So the idea is, does it stop where it's at, or does it slide back down? And that is going to have to do with, so we have, we'll do something like, no, I should probably use a different color. Whoop. Green? I like green. Force friction versus force gravity. And then, because we'll be using it, I'll put in force normal. So force gravity is mg sine theta. We can figure that out with this being theta, drawing a line here, do some geometry, and we can see that this force, if this is gravity right here, then this would be mg sine theta. I'm not going to show you how to derive that. You can if you will. I recommend not, because it gets confusing enough that you might make a mistake, and you're much better off just memorizing that the force of gravity going down a ramp is going to be mg sine theta. I would like to remember sine for sliding. Okay, force friction will be mg cosine of theta times coefficient of friction static, which is like, I think 0.52. 0.52 right there. So we want to see which of these is bigger. I'm actually going to look at force gravity over mass times gravity and force of friction over mass times gravity, because they both have gravity, and I don't really want to set them equal to each other because they might not be equal. And I'm going to just divide both sides by mass times gravity because, well, it's the same mass times gravity. It's kind of like canceling it out, but not really. So we want to see if sine of theta is bigger or cosine of theta times coefficient static friction is bigger. So sine of 35 is, make sure we're in degrees. We are in degrees. Sine of 35, I know I don't need the close parentheses. I'm going to put it anyway. 0.574. 0.574, okay? And then we have 0.52 times cosine of 35 degrees. And that's 0.426. 0.426. Make sure I got that right with the 0.52. I did, 35 degrees. That's also correct. So what this tells us then is that this is due to gravity, basically sliding down. This is due to friction. And since gravity is, the force due to gravity pulling it down, this guy right there, is bigger than the coefficient static friction, it's going to slide down towards the bottom of the ramp. And then once it gets to the bottom of the ramp, it'll slide all the way across. So slides all the way down the ramp and back across the frictionless horizontal surface. So one of the reasons I wanted to divide by mg over here, just in case you're curious, that's just fewer things I had to put in the calculator. I could have left them both in here and then would have scaled both of them up. By dividing my mg, I put fewer clicks in the calculator, and I'm less likely to make a mistake. So that's how I approached this problem. If you kind of look at it, I did kind of a conservation of energy. It's like we have this much energy to start with, we have this much energy we end with, potential-wise. We find out how much energy we lose to friction, and that eventually told us the height that the block reached. Then when we came down to see if, like, well, the block would stay there, we looked at the coefficient of frictions. So when it's moving up the ramp, we use kinetic coefficient of friction, i.e. moving. And then static, when it was stationary, we use the coefficient of friction for static coefficient of friction. So I hope that helped. I will see you next time.